Uh, Honorable President, Honorable Vice President, distinguished council members, esteemed fellows and associates of West Bengal Academy of Science and Technology, esteemed colleagues, and all honored guests, and all other members of academic community. On behalf of West Bengal Academy of Science and Technology, I extend a very warm welcome to each one of you. Now, this academy was conceived in 1986, registered in 1989, and since then, for last 38 years, we had this AGM held in IICB Auditorium. But then last year, we had to have this AGM in ISCS, Jadavpur, and this year we are here in the IIT Research Park. And so I begin by thanking the directors of these institute, Professor Kalobaran Maiti and Professor Shuman Chakraborty, for their unconditional support in having these AGMs. Thank you very much. With this, we declared this AGM 2026 open. I now invite on stage our president, Professor Shivaji Chakraborty. Professor Chakraborty, may I request you kindly to join me on stage? And it is my honor and privilege to invite on stage a scientist whose presence actually elevated today's AGM. Dr. Sridhara Panikkar Somanath, former chairman of ISRO. Dr. Somanath, may I request you to kindly join me on stage? Dr. Somanath, thank you very much for accepting our invitation. On behalf of all of us, please give him a warm welcome. May I now request Professor Chakraborty to greet Dr. Somanath with a flower bouquet on behalf of the Academy.
Let us all three hold it.
Okay, we now move to one of the most cherished traditions of this academy, the annual oration. This is the moment when we deviate from this administrative rhythm of AGM and turn our attention to scientific journey that would inspire and uplift us for the next 1 hour. It is my great privilege and honor to introduce Dr. Sridhara Panikkar Somanath, one of India's most distinguished space scientists and a visionary leader who has played a defining role in shaping the nation's space program. Dr. Somanath served as the chairman of Indian Space Research Organization, ISRO, and Secretary Department of Space from 2022 to 2025. An eminent aerospace engineer with nearly 4 decades of service to India's space missions, he is widely recognized as one of the principal architects behind the historic success of Chandrayaan-3, which made India the first nation to achieve a soft landing near the moon's south pole and the 4th country in the world to accomplish a successful lunar landing. Throughout his remarkable career, Dr. Somanath has made pioneering contributions to launch vehicle engineering, propulsion systems, structural design, and mission integration. He previously served as the director of Vikram Sarabhai Space Center and the Liquid Propulsion System Center, where he played a key role in development of India's PSLV and GSLV launch vehicles. Under his leadership, India's space program achieved several landmark milestones, including Chandrayaan-3, the Aditya L1 solar mission, advances in the Gaganyaan human spaceflight program, and next-generation launch vehicle technologies. Only yesterday, India's Chandrayaan-3 lunar mission has been honored with the extremely prestigious 2026 Goddard Astronautics Award by the American Institute of Aeronautics and Astronautics. Please give them a hand. Dr. Somanath stands in the proud lineage of Sarabhai, Dhawan and Kalam, carrying forward their legacy and distinction. Now, for many of us, the moon landing of 1969 or the breathtaking images taken from Artemis were awe-inspiring. But nothing compares to the pride of watching our own nation rise to the skies and the privilege of meeting the architect of that achievement. Ladies and gentlemen, fellows of the Academy, it is my honor to invite Dr. Somanath to deliver the annual oration.
Can you switch all these lights? Yeah, done. Okay. So, am I audible? Yeah. Okay. So, good morning, all of you. It's a great privilege. I had to be careful because. Okay, thank you so much, and good morning, all of you. It's a great honor to be part of this annual general meeting of the West Bengal Academy of Science and Technology. Thank you, Professor Shivaji Chakravarti, for inviting me. So this gives me a great opportunity to come to Kolkata and to see the great stalwarts of your academy, and really, for me, it's a great honor. So thank you so much for enabling this to happen. And Professor Shivaji told me to talk about Chandrayaan-3 story. That's all he told me. Then I saw the title. I think the title is very interesting. It's We Are Precision, Perseverance and Innovation of Chandrayaan-3. Of course, I put a story like this about landing and science. I think all of these terminologies which you have written in the title will appear in the presentation. So, though I have not given the title precisely in that direction. So, what I thought that I will quickly speak about it and possibly have an interaction if you so desire, maybe at the end. So, I am given 1 hour of time to speak. So, let me start looking at what you are seeing here is an animation of the rover that came out of the Chandrayaan-3 lander. And this animation was prepared well in ahead of where we actually had that visuals coming from on board. And I couldn't ever believe seeing it in reality, that image being transmitted from on board. So this we have seen many times, but then seeing it in real life is really such a great experience at the control center. So the talk will be centered around the Chandrayaan series of missions, not just Chandrayaan-3, the making of the Chandrayaan-3, the mission operations and preliminary outcome. But while I speak about it, it's very interesting to speak about Chandrayaan-1 and 2 as well, because they paved way for the Chandrayaan-3 to happen. Just now you were mentioning that as architect of Chandrayaan-3, I do not take any such roles. I am not an architect of Chandrayaan-3 or neither Chandrayaan program. I had a great opportunity to head the organization at that moment when Chandrayaan-3 was in making. In fact, for us, it's a journey that spanned many, many generations of leaders, starting from a person who actually envisioned that we should have a Chandrayaan program, like Dr. Madhavan Nair, who was a former chair, and many other leaders who came, built it, and made this thing to happen. So I am in the lineage of all those leaders. I had a role to play while Chandrayaan-3 was happening. And specifically the role was in terms of making sure that this time we do land. I think from that context, of course, I take the responsibility. But then the whole of that was envisioned as part of our organizational envisioning the long-term moon program. And you will also hear at the end that we are not stopping with Chandrayaan-3. We are having a long-term further plan to look at moon as one of the places where we should explore, understand. And the next generation of people will definitely take on that job and make it happen. So the evolution of Chandrayaan happened with Chandrayaan-1. So this was a time when Dr. Madhav Nair, who was the chairman at that time, was looking at why don't we even look at how to go to moon. And we had no rocket at that time. The rocket that we had only PSLV. This can lift only hardly 1 ton plus a little bit to a polar synchronous orbit. And this idea of sending something to moon was not easy because we need to find how to send a significant mass, because unless you put sufficient mass, you will not have enough fuel to go there and land or even orbit there to be captured on the moon orbit or even do some meaningful scientific experiments. But still, we worked on it and came out of a method by which that we can actually put it in a large elliptical orbit, slowly raise it to reach the moon orbit and then capture it on the moon using a very energy efficient approach. I think this is something very unique others have not done in the past. So we were able to do a mission with PSLV rocket to go to moon. And Chandrayaan-1 was really momentous in its accomplishment. I will show you that in terms of finding new science from moon. And Chandrayaan-2, all of you know that where I had a role to play in terms of the rocket that we are building and also the propulsion that we are developing for soft landing. Of course, this couldn't achieve that purpose of soft landing, but that was really achieved using Chandrayaan-3. And that's got all these awards. And this AIAA award in the recent Goddard Award is something that came in the last of the awards. It received many, many awards in the past for most of those scientific organizations across the world. Now, Chandrayaan-1, when we were envisioning how to do it with PSLV, the approach I mentioned, but the real scientific payloads which are to be put in moon, such a moon probe, the entire mass of the satellite was hardly 1.1 tons. And we have the mass of the payload, that the instruments that are supposed to do the measurements was hardly 20 kilogram. You can imagine that much of the satellite is propellant because we need to travel all the way up to the moon to be captured on the moon to bring to a circular orbit. But then what really happened is once we were building that satellite, a suggestion came from Dr. APJ Abdul Kalam. He was the president at that time. He said that when you are going to moon, don't go empty-handed. You must put something on the moon, as an Indian flag should be placed on the moon. And that direction was given just 6 months before the launch. Then we had to build something called a moon impact probe. And that was put as an attachment to this probe, main satellite, and with a separation system so that we can throw it on the moon surface and do some measurements on the moon's surface while it is descending. While it is descending through the atmosphere, the so-called atmosphere. There is no atmosphere on the moon, we know that. But then it actually produced so much of data, especially the presence of hydroxyl molecules in the upper layers of the moon. That was one of the earliest findings. And many of the payloads in that Chandrayaan-1 was actually not made in India. We made an announcement across the world that you are free to donate us the payloads, and we can host it on the moon probe and then find new science. And today you know that the first ever discovery of hydroxyl molecules on the moon was actually done by an American instrument. And then later, an Indian instrument discovered it. So from that context, many of those accomplishments of Chandrayaan-1 is really phenomenal. And some of the findings of the Chandrayaan-1 is really something which is interesting to go through. For example, there was a belief prior to that, even after many people went to moon and landed on the moon, Americans, Russia, and China, I think they were all exploring moon by the time. But some of the new findings that came out of the moon missions really phenomenal, especially the moon is bone dry. And the interest came much more stronger to go to moon because we now discovered water on the moon. And today we know the water is not just a trace material there. It is actually possibly abundant deep beneath the surface. This is something currently being postulated and to be discovered yet. Then moon was supposed to be very geologically dead billions of years ago, and we now know it's no longer. It's a dynamic and a volcanically active body. Though there are no visible volcanoes, must be internally active. Then there are other findings. For example, moon's regolith absorbs most of the solar winds and protons, but that's not the case. Similarly, the lunar wake. Lunar wake is something that you face the sun and the backside of it you see the wake. And this wake is devoid of all solar influences. That was the belief till then, and it is also found to be wrong by Chandrayaan-1. Then there are worries that will you ever be able to go to moon and then settle, create a settlement? Because you see, in the absence of atmosphere, there are a lot of impact happening on the moon, and it's not safe for anyone to go and settle there because of this. So, but the current understanding of the moon is that there are buried sites and the interconnected tunnels on the moon that possibly human beings can actually go and settle, where you will be safe from such impacts as well as radiation. So, some of these findings came out of the Chandrayaan-1 time, that is 2008-2009 time frame. Similarly, the moon impact probe, this was the first probe from India which actually impacted on the southern pole of moon. Not before, even before Chandrayaan-3 landed there, if at all anything that India put on the moon was, it was farther south of where Chandrayaan-3 actually landed. So, we must give credit to Chandrayaan-1 for putting something on the moon surface very close to the pole. And it actually impacted very nicely, though, you know, because it is descending at a high speed, it would have crash landed and wouldn't have survived. But then during the descent, we had a camera, we had some instruments which actually measured. We have beautiful spinning images of landing on the moon, and also have detection of this early detection of the water vapor on the moon. Okay, this is repeat. Now, today we know that the discovery of water on the moon came from the payload called M-Cube, which is a mineralogical payload from US, but then Indian instrument also detected. Today we have a map. The picture that you show is a concentration level of the hydroxyl molecules on the distributed on the surface of the moon. And we know today the pole of the moon carry more water than on the equatorial regions. Another interesting observation from the payload called SARA, which actually looked at the wind, solar wind protons, which I told earlier, the hydrogen high energy, energetic neutral atoms in the wake field of moon. And this was something very interesting feature which was published, and it actually caught a lot of attention from the global community. Because we were moving around the moon and that could do the measurements on the farther side, on the wake side of the moon, and specifically from this payload, these observations could be made. Again, the iron population on the lunar wake was also found out from the time spectra of the observations that we did from the same instrument. Not only the surface hydroxyl molecules elements were found out, but also the presence of hydroxyl molecules on the atmosphere of the moon was also detected using our instruments. For example, the exosphere of the moon also contained water molecules. And all of you know that why the moon is not having an atmosphere, what made the atmosphere disappear, and whether there will be any way that you can actually recreate atmosphere on the moon. These are questions which are being debated, discussed, and what geological activity that actually made the atmosphere vanish. Is it from the solar radiation or pressure or impact? There are many questions, but this is an interesting thing that there is continuously loss of volatiles and material from the surface of the moon to the atmosphere, and it is actually measurable. And actually the water on the moon was detected not on the surface of the moon first time, it is actually detected on the exosphere layers on the moon using this instrument for the first time. Now coming to Chandrayaan-2, I think the interest on Chandrayaan-1 was really very, very good in the scientific community. But then continuing in the Chandrayaan-1 mode was not really going to bring us any benefit, because we are not going to have any in situ measurements. Most of these are remote sensing type of measurements. You are going to the atmosphere and actually probing the surface. But by the time a new rocket was in place, the LVM-3, because PSLV can lift only hardly 1.1 tons, but now we have a new launch vehicle, the LVM-3, which is capable of lifting almost 4 tons to orbit. So this gives a great possibility for us to design a craft with an orbiter, lander, a rover, etc. And this rocket, for example, I was a project director, the first project director who actually made the experimental launch, and later the cryogenic engine development and making it operational. But by the time the Chandrayaan-2 was conceived and ready for launch, the LVM-3 did only just 3 missions. And the 4th mission we have to carry Chandrayaan-2. I think any spacefaring nation will not take the risk of putting a high-cost mission, scientific mission on board a new rocket which is not yet declared operational. So we were only doing the qualification launches, and the operational launches are yet to happen. But then we decided jointly within the organization that we are going to send this craft on the moon, and I am really thankful to the chairman at that time, Dr. Shivan, who allowed me to make that decision and get implemented, because there were a lot of worries internally, but we said that we will make this rocket succeed this time. When the spacecraft was designed, it was designed with a landing capability. As you know already, the Chandrayaan-3 and Chandrayaan-2 are very similar. We will go into the engineering details of that and how we built that satellite with its orbiter lander. So by the time this design was going on, I moved from VSSC, Vikram Sarabhai Space Center, Liquid Propulsion System Center. So one of the tasks given to us was to design an engine which is going to make us land on the moon. So we need an engine which is throttleable. You know, liquid engines are generally constant thrust engines, and if you want to vary the thrust using an algorithm, it actually poses a lot of problems. So we had to develop that engine with the first time we developed a throttleable engine where you can control the fuel and oxidizer flow, and then make it lower so that it actually do a soft landing with a velocity less than 1 meter per second. So I'm very happy that at that time we completed the development and became part of the Chandrayaan-3 propulsion unit. So the contribution in building the rocket as well as the orbiter, lander was something very phenomenal. But today we know that Chandrayaan-2 made such an important contribution. The specific contribution, though it couldn't actually land safely on the moon, is in terms of its ability to do an imaging on the moon. The orbiter continued to work for many years, and then it produced one of the best ever images of moon today. So we have 25 centimeter resolution images of the entire moon today, and these images are actually used by other spacefaring nations, including US in its recent missions, Japan and Russia and others. We were able to supply this data to them, so they were able to use this data for their planning purpose, location identification, as well as the trajectory planning, which are based on vision. So that way we contributed to the global interest in moon missions. Possibly after the Artemis 1 mission, I think there could be better images with the US. We'll have to see that. But as on today, in the public parlance, we can see that Chandrayaan-2 images are the best of images that are available at the moment. Now coming back to Chandrayaan-2 scientific results, the earlier finding of the hydroxyl molecules presence, etc., were confirmed by the Chandrayaan-2 because we had no lander, and the lander crash landed at the soft landing attempt, and we had left with only the orbiter, where there were certain amount of instruments on the orbiter. Using that instruments, we continue to do the scientific studies, where there was still an instrument to look at the water molecules, and it was again confirming it, and also confirming the mineral composition of the rocks on the moon, which is again similar to that of Earth. For example, silicon-based, calcium-based rocks were still discovered there in abundance, which actually says that there is some questions on the origin of the moon. Now, where from the material, the nature of the material on the moon and the nature of material on the Earth, whether they are similar in nature. You know that it cannot be exactly similar. It actually varies from location to location, but still you can make a reasonably accurate assumption based on the measurements that it actually originated from earth-bound materials, not really came out as a separate object and got captured on the orbit of the Earth. I think this was a basic question which was still being discussed. Another interesting finding came from Chandrayaan-2 was the distribution of sodium on the moon using an instrument called CLASS on the Chandrayaan-2. So sodium in the form of its constituent minerals, which actually changes with its day and night characteristics, and its concentration also changing from the equator to the pole regions, where they have an unsymmetry in the north and south pole also. I think all of this were part of the significant mapping of the minerals using the remote sensing capability of the Chandrayaan-2. And I said about the image quality. So we have wonderful images of the Chandrayaan moon surface, and the sharpest ever images, which include looking at some of the landing sites of other missions, taking better images of the craters and boulders. And many of these images helped us in planning the Chandrayaan-3 orbital landing site locations much better later. We also had analysis of the boulders distribution across various landing sites, which gives you much more clearer perspective of the size of the boulders, Because if you have to make a soft landing, that we need to keep away from the boulders, dense areas where there are boulders in large numbers, you will not be able to find out places to soft land properly, because if you end up with some of the legs touching the boulders, you will end with a tilt which is exceeding the limit of the lander. It may topple, which actually happened for many of the landers which were landing along with us. I think this information was so crucial to ensure that we actually land at a place where the boulder distribution is actually manageable for us to decide on the better location. So this was done using the images, and all this was going on while Chandrayaan-2 images were coming to us. Another interesting, very interesting finding from the Chandrayaan-2 was that buried craters. I think this also created globally, there was a lot of interest coming out of it. Actually, there are craters, but over a period of time, soft material like dust material cover it, and you do not actually see them. And this can be seen only with a type of a lidar or radar imaging, which actually penetrates deeper. And you see the density variations, and you can actually make out these. These are not really the hard surfaces, these are soft surfaces which exist. And there could be a crater which over a period of time material got deposited and covered it in a manner that it's no longer detectable from that point of view. I think, on Earth also there are many craters, which over a period of time you don't even actually see them. Cities possibly covering, but there are natural craters which are available as proof of meteorite impacts and of large size on Earth also. I think the same, I'll skip this. Similarly, there are many other findings. For example, the distribution of argon 40 is another very important discovery in the upper atmosphere of the moon, which actually showed the origin of argon and where from it is actually originating in the geological processes. And this was such an important discovery as far as the decay characteristics of materials within the moon regolith or the rocks were interesting aspect to be studied. So similarly, a corroborative measurements from other instruments from other payloads of international payloads were also done during this time using Chandrayaan-2 mission. Now, for all of you would definitely ask what really happened in Chandrayaan-2 and why didn't actually soft land. I think this is something very important for all of us to understand, and how we made that Chandrayaan-3 land successfully. So this was very interesting, because by the time this the soft landing could not happen, we constituted a failure analysis committee. We went through the reasons why the soft landing could not happen. But then in a community like this, I cannot give you the very precise answers of what exactly went wrong. You have to pardon me, except that you want to know very specific answers. There is a community which is heterogeneous community in terms of or describing what went wrong. But in a simple way, if I were to tell you, there were many failures. Okay, that there is a principle in engineering. Things go wrong when all windows align. There are protections against propagation of failures. If something is not done properly, it is actually stopped by a protection somewhere. And if that protection is not there, it actually propagates to next level. And then there is a protection. If that is also not there, it propagates to next level. So if you align a failure path is aligned in that all windows are open, then it actually manifests in terms of the real failure. It's very classic aspect of engineering designs, and how do you really prevent a failure to propagate, not to propagate. I think when you are designing systems, you understand this, and that's why we take care of margins. Design margins you build, you build redundancies, you build algorithms that you take care of possible excursions of bounds of performance, and then take care of it by some approaches. You also build sometimes an alternate system in case of this primary system fails, not the actual redundancy, an alternate system to handle failures. So when you look at all of this whole failure of Chandrayaan-3 to make a soft landing was actually very simple failure. When you say simple, it's not that simple. Simple is from the context of when you actually look at this point in time and then look at it, it looks very simple. And it was the case for most of the failures of the world. And you see that space shuttle failure, when an O-ring really failed, why engineers did not even understand that O-ring of rubber could actually become brittle when the temperature goes down. It's such a simple knowledge, but then people ignored it. And there was a failure in PSL with first flight failure, where we made the signal got reversed when you had a division by a 0. In a computational, in equation, when you end up with this, the denominator becoming 0 due to computation, you know that it ever happens that you are ending up with a problem in computation. So the signal reversal will happen and the whole control is lost. Similar to that, we also had a problem in this. One of the important problem in the Chandrayaan-2 was its software. What was sitting in the onboard was not exactly like the one which was used for simulation. So there was an error sitting in the software, which actually manifested only, and it won't manifest all the time. It will manifest only in one condition of something happening, reaching a threshold, then that error will come into the loop and cause all the trouble. If everything is nominal, nothing will happen. And this is a very classical case of software testing. I think possibly people know that if you do not take care of extremities of testing in bounds of parameters, you may not ever find out the integrity of the software. That's why even with a working software, you will see that many years down the line, problems start manifesting. I think those who are working on softwares and standards, you understand this. This was one of the issues. Second issue is that you start taking assumptions. And we found out that when you engineer something, you start discussing assumptions. And you put self-constraints which are not imposed by the system. You artificially constrain things. And this is a very, very clear case of discussion which is required and debates required in systems where, why did you actually constrain yourself? No, I have not put that constraints in front of you. You yourself artificially constrained it. One of the artificial constraint was when the spacecraft is moving, you know that it will be subject to rates. We call it rates, degrees per second in different axes. You don't allow it exceed certain thresholds. And if it exceeds threshold, you will clamp it at that point. And you generally do this for very wide value than what is expected. Suppose it is going to have 2-3 degrees per second, you may put it at 20 degrees per second. It is 10 times of it. And you think that it will never exceed. This is again a wrong thing, because if there is no reason to put a limit, you should not put a limit. And we found that if you had not put a limit, then the mission would have survived. We found that the mission would have survived even if the software error was existing, even when a bound was put, unwanted bound. But there are chain of such things which existed in this, and this actually made the landing into failure. But I can tell you that it doesn't mean that now Chandrayaan-3 landed. I can't guarantee that software was perfect in that. It actually happened in such a way that it worked in the nominal conditions which actually didn't trigger any failure scenarios. And this is very important for everyone who engineers complex systems to understand. It doesn't, one-time success doesn't mean that everything was perfect. And we know it very well. In space engineering, it is such an important thing to realize that making one-time success is never a success. You need to do it over hundreds of missions, extending over large parametric perturbations. I think those who are dealing with statistics, the distributions of parameters, its bounds, and how combination of bounds can actually trigger a complex failure scenario. So I told the reason for failure in a very simple way in what I can do, but then the real problem of the failure was still not revealed even after the failure analysis. Then this is an interesting story. The real problem of the failure was none of this. It was in terms of two engines. There are multiple engines in the craft, and these engines are actually, we will show you the engine and show you how it functions. And these engines develop thrust. And if you do not balance the thrust perfectly, you will develop a differential thrust and it will cause the vehicle to rotate. And this controlling the thrust was using an algorithm and a motor drive valve, and there was an issue with respect to this drive, causing the motors to behave differentially, causing the thrust to be higher in one over the other. And there was no way to control it. And this was a primary failure, but it was never even discovered during your failure analysis, because the measurement showed it is equal. So there is something which is going beyond the measurements, and this was by a ground test simulation which we lasted for years together, almost 3-4 years we took to find out what went wrong, and it got revealed to us at some point in time, and then that correction solved the entire problem of Chandrayaan-3. But then when we were looking at Chandrayaan-3, we were looking at what all heritage of Chandrayaan-2 we need to take, and how do we really improve to make sure that there are no unknowns in the new Chandrayaan-2. So we understood that Chandrayaan-2 orbiter did most of the work. So we said that don't put unnecessary instruments in Chandrayaan-2 orbiter, move it out and minimize the complexity of the orbiter and put more into the lander. So we made the lander much more stronger. We put more fuel in it. We worked out on newer algorithms. We did new instruments, developed new instruments. We strengthened the whole thing. There are many such improvements which happened, which I will discuss you, and what made the soft landing possible. Now, Chandrayaan-3 was a return to moon, again with the same objective of going to moon and then landing. And the phases of missions which we designed from liftoff to reaching the moon was exactly the same. There was no difference. The whole algorithm which was perfected in going to moon and capturing the moon, it was proven in Chandrayaan-1, it was proved in Chandrayaan-2. So we resorted to the same approach, put in a large elliptical orbit around the Earth, progressively burn the thrust, fire it at the perigee, raise the apogee, so as to the apogee to reach the moon and get captured on the gravity field of moon, then slowly reduce the elliptical orbit to circular orbit and then land. So this approach was same, but when you do like this, it takes long periods of time. Recently when the Artemis went to moon, how many days they would have taken to reach moon? Maybe 4 or 5 days. When human beings are involved, you need to go very fast. But there were no human beings, so you could have taken longer periods. So we took almost 30 plus days to travel and reach on the moon. That was okay. But when you really send humans to moon, we can't do this approach. We need to make much more powerful rockets, and heavier payloads are necessary if you have to send human to moon. Now, let me go to the making of the Chandrayaan-3. The Chandrayaan-3 had the constituents were just the same, the orbiter, the propulsion module. The orbiter is now called the propulsion module because the orbiter had no high resolution camera. It had no instruments to measure what we did in the Chandrayaan-2 because Chandrayaan-2 orbiter was still working. So when you sent Chandrayaan-3, there was no need of really an orbiter. But then we need an orbiter to reach there to carry the propulsion to reach the lander up to the moon orbiter. So there was something called the propulsion module. There we could actually maximize the propellant loading so that in case of any propulsion issues that we should not miss reaching the orbit. Similarly, we strengthened the lander and rover substantially, and the strengthening details I will tell you what all we did. If you look at the improvements, there were many improvements in terms of engines. For example, we had 5 engines. We reduced 1 engine and made it just 4 engines, primarily with the algorithm change and also mass reduction on the lander, so that we were able to manage the landing with just 2 engines instead of a central engine approach. The entire guidance and algorithm was modified in such a manner. I will give you one example. How do you look at guidance algorithm? So assume that we are going to land at one point on the moon at that point. At that point is already marked. You know the latitude, longitude, and where exactly we are going to land. And while we are doing the landing attempt, the algorithm understands that I am not in a position to land there due to my time available, fuel available, or the altitude change which actually happened. And if I try to attempt there, then I may tip off and fall and fail. And if the algorithm understands that it should actually land here, where I am able to land safely. So the safety became more dominant parameter than accuracy. So this is a very crucial decision. I think this decision in the algorithm was very important. In the Chandrayaan-2, the algorithm demanded that it should go and land there, irrespective of whether the safety of the mission is compromised. I think such debate and discussions in the internal thing changed the entire guidance algorithm. And we also tied up with some of the professors in Indian Institute of Science and others to bring on board their simulation capability, mathematical capability, train our young people, engineers within the organization to look differently in the algorithm development in guidance. And that actually helped us in terms of building it more robust algorithms. Similarly, we improved the power capacity. When you go to moon and go to the South Pole, the sun is not that bright there. If you look at the stand at the South Pole or near to South Pole and look at the horizon, you see sun rising on your left, going over and then rest. It actually going down little later. So you don't actually go like what you see the sun on the on the equator. You go to a pole and look at the sun. Sunrise and sunset. It actually happens for some time, and you will see it at a very low elevation. So the ability to produce energy in the southern half is actually very less. So the solar panel should always face that location. If it actually faces in this direction, then it is impossible to turn the craft and then make it look at the sun. So you need to ensure that it actually lands precisely in that orientation looking at the sun. If it actually misses, the mission is gone. In just one day, the battery will drain and mission is down. So we have to look at failure scenarios like that and how to have a protection. I think you know the Japanese lander, which actually went just few months after that we landed, ended up in landing in a reverse direction, so that it was dead in just one day. So unless you foresee what are likely to happen, that you won't be able to protect it. Another improvement that we did is in terms of the landing legs and its ability to handle shock. For example, if you actually land, we supposed to land it with 1 meter per second velocity. When we designed it such a way that even if it goes to almost 3 meter per second velocity, it will still land without breaking its legs, damaging its constituent components, and still be able to do experiments. So this was the strengthening process. And we added new instruments on board. When something is traveling on the moon orbit, you need to measure velocity. Generally, we measure velocity, direction using inertial sensors. Rate gyros, accelerometers are used on board to do that. And we also had cameras which actually look at the surface, and using the camera images, you can compute the velocities and positions. Then we added a new instrument for Chandrayaan-3 called laser Doppler velocimeter, which actually sends 3 laser waves, and using the reflected Doppler from the laser, we were able to compute 3 constituents velocities. And this was very critical for us. And for the Chandrayaan-2, we did not have this instrument. In fact, we tried to buy one from the West, and no one supplied this instrument to us. It was extremely costly. Timeline was out. But we took a decision that we are going to develop it in India and put it on board Chandrayaan-3. And it was done in 1 year time frame. That whole instrument was developed, and we put it on board. Similarly, there were many such small improvements which actually made Chandrayaan-3 significantly different from Chandrayaan-2. And all the software errors were removed. But then what is more significant for Chandrayaan-3 was not just all these improvements. It's the testing that we did. And the test program ran for almost 1 year. After the first year after the failure of Chandrayaan-2, we did the failure analysis. Second year, we found out how to modify. Third year, we actually realized the entire proto qualification hardwares. Then we ran tests for 1 full year before we built the final version. The test ran through hundreds of simulations, including helicopter sorties, balloon sorties, free flight sorties, on-crane simulations of zero gravity conditions, drop test, propulsion extremities test, and also software simulation test beds. There are thousands of tests that was done, and all these data were analyzed. And this was something which was lacking in our Chandrayaan-2 time frame, the extent of test when the extremities, especially parameter perturbations were, and similarly when hardware, software, and systems come together, they don't play very well. One of the example is this. We actually created a lunar simulator on ground, created a long area where craters were built. Then we were able to fly on top of it using a helicopter. Of course, helicopter doesn't simulate the type of speeds that you see when Chandrayaan-3 is landing. Chandrayaan-3 is moving at almost 1,000 meters per second type of speed, whereas helicopter won't move at that speed. But still, you can do that experiment in terms of instruments. We put all the instruments Chandrayaan-3 electronically inside the helicopter, put all the viewing instruments at the bottom side and flew over the areas and simulated the algorithm whether the hardware is responding, sensors are responding to that type of processes. Another interesting test we did is hanging in a crane which is almost 100 meters tall. And the entire propulsion module was hung using counterweight system so as to offload the gravity. But of course, gravity cannot be easily offloaded using counterweight systems, but still a closer simulation. And then by the time the dynamics set in terms of the cable and suspension, there are some errors coming, but then we can model all of that and then capture that model and then find out how the control system respond to such propulsion behaviors. So this was crucial to see. Simulating the landing on Earth is actually extremely difficult. Gravity is a field force, and field force cannot be taken away. Whatever you do, it will be still there. Even if you put a counterweight, it will be still there. And the effect of air in terms of its dynamics that getting modified due to small drags that come. And another problem is its mass. Even if you put a counterweight, the thrust of the engine is so small. Gravity on moon is. I think it's okay. The gravity of the moon is, am I okay? Is audio okay now? Yeah. See, the gravity on moon is 1/6, and whatever you do on Earth, I think you cannot actually simulate the 1/6 scenario on Earth. You can actually put a counterweight and remove the gravity, but exactly simulating 1/6 is not possible. So under these constraints, the simulations were done, and we were able to make good sense of the dynamics, but rest was left to the mathematical modeling and simulation only. Now let us look at some of the simulation testbed videos. So it will look like a very complex cabling and assemblies inside the helicopter. We actually flew these helicopters for so many sorties. Getting a helicopter and from Air Force and then running the sortie itself was a great tough job in terms of their schedules. And craters of this nature were built where we captured the images using this and then try to see whether that is capable of identifying the landing locations. But they are not exactly like moon. Of course, we can't create the moon reflectivity, the surface characteristic, etc. At least geometrical features could be detected using these cameras. Now what you're seeing is a propulsion test where we hung it from the crane with a counterweight system and then see the engines firing, the control thrusters firing. This is a tie down test and this is a hanging test. Okay, this doesn't move now because we are tying down the whole thing. And when you are actually firing it in the hanging conditions, the craft is made in such a manner that the thrust is exactly equal to the mass so that we can balance it at a near neutral conditions and see its dynamics. But then you know that dynamics will not be exactly same because the real hardware is not exactly the same as that or the one which is under testing. And this whole facility was built at Sriharikota. This is the landing site where we had the landing location and the crane facilities where the craters were also there simulated. This is yet another test facility with the crater simulation. Okay, this shows a test on the landing lugs, which has its own crushing energy absorbing systems with the honeycombs and dashboards, which actually can absorb the impact energy. And hundreds of tests were done at different inclinations, material characteristics, regolith densities, to see that it actually survives impact without causing undue shocks. Okay, so this was done in simulated structural hardwares because I am not in a position to show the exact engineered hardwares in this video. Okay. So finally, we built the Vikram lander. The Vikram lander now stands almost 1.7 tons with the rover because it had a lot of fuel primarily required for decelerating, bringing down the orbit as well as landing time. And it's quite a big lander compared to many other international landers. And the rover was much more cute. It's 26 kilogram mass with 6-wheel rovers, the rocker arm type of designs. But the most important part, it contains 2 spectrogram, one based on laser ablation. A laser will be sent to ablate the material on the surface, and using the ablation you can do the spectroscopy. Another was with an alpha particle generator, which is a radioisotope which was put there with the help of our atomic energy people, and we put that on with a alpha particle emitter, and that was used to do the spectroscopy. So 2 spectroscopic instruments were on board on the simple payload like this with its communication, power generation and other capacity. Also commanding capacity to from the ground that was available. And the launcher was just the same. The LVM-3 in its next mission was ready for the launch. But I can tell you before this launch, we were also done some more launches of commercial launches. Hence we were approaching this launcher with much more greater confidence, not like what we did for Chandrayaan-2 at that time. Now looking at the mission operations, the journey from Earth to Moon was similar. There was no much difference compared to Chandrayaan-2 or even 1 in terms of putting it in the orbit of Earth, raising the orbit and then reaching the Moon and getting captured. And the Chandrayaan-3 got captured on the Moon surface on 5th of May, 2023. And we go through a elaborate chronology of events that will actually take it to Moon. I think it is so precisely to be done by using measurements with the support of the global players. I think this is something which I want to tell you, that Chandrayaan-3 cannot be achieved by India alone, and we need a global coordination and support. So we took support from various players, including NASA, ESA, their ground stations, their tracking support, their data flow into our system, and then verification of the data and orbit precisely are necessary to achieve this type of missions. And one of the reasons for our success in Chandrayaan-3 is primarily enhanced landing area. Earlier in the Chandrayaan-2, we defined a very small area for landing because the data available in terms of image quality, boulders and craters were not good enough for us to plan for a much better area. So we decided that we will plan a longer area because we have now the high resolution data. And this allowed us to land anywhere in the larger area, which will actually remove much of the uncertainty in terms of rates exceeding or fuel not enough, etc. So this could handle that aspect. And the landing happened. I think all of you would have watched it live on the TV on that day, that 23rd August it was landing. It was really a phenomenal thing to see. But I can tell you that we planned so many contingencies in this landing and what will happen at each of these events. From lowering from a 100-kilometer orbit first to a 30-kilometer by 100 elliptical orbit, progressively bringing to a position where it is actually vertically above the landing site, and then bringing down slowly at a given rate. And if you do not find once you are closer with your camera, you see that it is not good for landing, you should be able to move laterally and then land another place. So all of these algorithms were built into it with its instruments. So there are dangers in this because some of the instruments may totally give a wrong data. For example, if you look at the radar data to measure the depth of the location, it may go wrong. Your sensors may drift, and sometimes that your cameras may not function. So in such scenarios, how do you really handle it? I think this is very core of algorithm design. In case of a multi-sensor fusion algorithm actually fails, how many sensors are to be taken, what options are required for us to land it. So we made sure, I think in simple terms, I will tell you that if every sensor fails, still it should land safely. This was algorithm, simple, in you put it. So we must do a blindfold landing, ensuring that it will actually land with a low velocity. And this was programmed as even zero sensor support. Of course, you can't do with zero sensor. You need to have some terminal sensors to ensure that it has actually touched down and engine should be switched off. So we even put a micro switch there to ensure that it actually landed, and a micro switch closes and engine can be shut down. To that extent, we designed such a way that this time it will be successful. And I can tell you that today, none of the sensors failed in it. Everything worked, and the entire landing was in the primary path only, and never a redundant path or alternate path were triggered in the algorithm. And of course, to do this, we need a lot of support across the world in terms of Indian ground stations and foreign ground stations. And I should thank many of those people across the world who are actually worked day and night to keep us feeding this data. Unless this data comes, Moon cannot be seen all the time from here, from India. It goes to the other side of the Earth, and we need to remain in continuity of communication to do such a mission. The rover was really doing very well. It actually traveled across the Moon surface for almost 100 meters, commanded from Earth. And in fact, it was about to fall into a small crater, but it was able to detect and prevent and then travel to another path. But it did. Its instruments, spectroscopic instruments, did wonderful measurement at multiple locations, and we have huge amount of data. We also had huge RF links. For example, the maintaining communication was very crucial. The rover should communicate to the lander should communicate to the orbiter should send the data to the ground in a seamless manner, both in terms of the data and commands. And this was achieved through multiple paths to make sure that in case of any path failure that we will still be able to communicate. Now, some of the scientific outcome I will quickly say and then conclude my talk. Now, we had primarily there are 6 instruments on Chandrayaan-3, Rambha, Chaste, ILSA, APXS, LIPS and SHAPE, and these names were abbreviations of the functions there. Rambha is actually a Langmuir probe which actually measures the electron densities at the very low ray height from the surface, and Chaste is an instrument which actually pierces into the regolith and then measure the thermal conductivity of the regolith by heating that zone and then measuring its response. ILSA is an instrument to measure moon quake. It's an accelerometer, triaxial accelerometer sensor which is deployed from the surface using a cable, and you can actually pull back and put back at multiple locations. APXS and LIPS are the spectroscopic instruments, one based on the alpha particle, another based on laser. And SHAPE is an instrument which is actually looking at a spectroscopy of Earth looking from moon to find out what are the spectroscopic characteristics of a planet which is actually living using its elemental composition. So, I told you already about it, and we saw each of them to be deployed at different times because we had only 15 days from the landing to the sunset. You know, sunrise on the moon is just for 15 days and you need to complete all the mission in 15 days and get to the data. So, it was done within that time, and then we produce fantastic results. One of them is on the elemental composition at the Shiva Shakti point. You know, the location where we landed was named as Shiva Shakti by Honorable Prime Minister after his visit to our control center after 2 days of our landing. And we had wonderful data which was corroborated with the earlier global data. Similarly, the mantle materials which were detected at that point were very primitive. This is another interesting data. So, I am quickly going through because I just want a few minutes at the later phase. We also measured a lot of ground vibrations using the sensors. This is one of the measurements which was not available from any other world level instruments, and there are a lot of discussions currently happening whether it is actually moonquakes or instruments noise or the rover movement. I think there are some discussions of the nature, but there are data which actually shows the moon is still very active. We also talked about the buried crater from Chandrayaan-3 landing, which I described some time back. There was an in situ measurement from the Chaste, which we pierced a composite probe into it with its own temperature sensors, and we found there is significant temperature gradient from the surface of moon to the depth of moon, indicating the conductivity of the regolith is actually much poorer than actually thought, which could be a reason for us to believe that future human habitation could be underground, where you can actually get a comfortable temperature where you can live without much heat loss. Because the temperature of moon goes to the extremes of high temperature and low temperature under day and night situations. So, you need to have good insulation capacity. So, that is the point that this curve shows. We also did a laser based breakdown spectroscopy on the surface of the moon, and the elemental composition of the LIPS had multiple locations, but all the publications have not come out. Even now still publications are coming out in this area which shows abundance of many of the elements, which includes sulfur, which was something which was very interesting. Why sulfur is appearing on the surface of the moon was a discussion, and sulfur generally comes only if there are some geological processes which actually drive sulfur from the underneath to the top. So, this gives a case for why there are some processes happening inside which actually push the sulfur to the surface. So, there are many topics of that nature, but other elements like calcium, iron, chromium and titanium are abundant like what we are there on Earth surface of Earth also. So, alpha particle APXS also did the similar measurements, and we have data of that minor elements which is very clearly brought out in this. We can see these publications in peer reviewed journals. The Rambha showed that the Langmuir probe showed the moon surface also has charged particles. There is no atmosphere, so electrons and other particles are there on the surface, and this knowledge of electrically charged particles on the moon surface is so crucial for future communication purpose. So, there are discussions going on, why don't you deposit some communication systems on the moon surface like a GPS equivalent based on moon, and this knowledge of this charged particle densities are very important to understand how moon can be used. And today we know based on the measurements that the density of charged particles is not that as strong as we have hypothesized, which is good. That future that possibly we may be able to put a short height transmitters of locations for possibly a moon-based GPS in the future could be derived, because that's very interesting topic which is under discussion under Artemis Accord. So near surface plasma content, which is same as I just mentioned. The spectroscopy of Earth was done by an instrument which was put on the orbiter, the propulsion module. It was not part of the lander, and the propulsion module currently is non-functional. So it went to orbit and it actually gone out of the moon orbit. It came to the Earth orbit, and then it is now currently back into the moon's orbit. So it's actually moving around the Earth-Moon system. And during this process, it actually captured much of the information required for it. Today, we have a wealth of information in spectroscopic side, looking at Earth and taking its spectral characteristics from an outside viewpoint. I think it's something very interesting. Possibly more science will come out of it when you look at exosolar planet and others. Now, after this moon mission, Chandrayaan-3 program was coming to an end at the 14th day. I asked my team, why don't you do something very different? Can we really reignite the craft and then take it to a farther away point? And this we discussed as a hope experiment. Why don't you just make a hope? But then my scientists were skeptical. They said that if you do that, we have only one more day. If you don't do that, it is going to be, you topple it and leave it on the moon surface for toppled. Why don't you? I said, anyway, it has done all its function. Let us do it. And we did a reprogramming done. And we did an entire simulation that night. And we loaded the new software into it and then reignited the stage. But then we did a very cautious short hop so that it doesn't topple. We just went up and then moved away half a meter away. The advantage is that when you do that, the entire location changes and we were able to repeat all the scientific instruments like the probing, the spectroscopy, the chaste at a different location, which could not have been done otherwise. So today there is a new paper which has come because it actually did at multiple locations, showed the spatial variation of thermal conductivity just because of that experiment. So it adds value when you do something beyond that we actually planned in the scientific. And I'm very happy my scientists did this and they were very successful in doing this OP experiment. You can read that article which has come yesterday in newspapers and TV. So Chandrayaan-2 was actually captured by Chandrayaan-3 in its landing location. We know that it actually did not stand upright. It actually toppled and then crash landed, but then we were able to take images of that also using Chandrayaan-3 picture. Now, I would like to conclude saying that the journey of Chandrayaan-3 is not the last part, though it's a series of missions that we planned in Chandrayaan-3. And while we were working on this, I had fortune to propose further missions to moon to the government and get approval. For example, Chandrayaan-4 was approved as a mission to go to moon, do a robotic experiments, take samples, pack it and send it back to Earth. I think this mission is fully funded by government and we are working on it. And Chandrayaan-5, which is a mission to deploy a rover which is 100 kilogram, which is much bigger rover, nuclear powered. But we have to build a lander to take that 100 kilogram rover up to moon and land it at exactly at the South Pole. And this rover will be built by Japan, JAXA, and the whole mission will be launched using a Japanese launcher. So it's a collaboration between Japan and India to go for a long-term 100 days survey of the moon South Pole using nuclear powered rover. So both these projects are currently on. We will be continuing this part. But we are not ending with moon alone, and we also have further exploration programs. One of them is a Mars lander, which is again an approved program. Before I left, I could convince government to get these programs approved, and also a mission to go to Venus. Venus is a very interesting planet where we have a very thick atmosphere, almost 100 bar. Sulfuric acid atmosphere, so how to penetrate and then look at the deeper into it and make a sense out of Venus and Mars. Mars and Venus are our sister planets of Earth, having similar mass, similar gravity, slightly lower than Earth, similar periodicity of rotation, but extremely different conditions. For example, Earth is a habitable planet, Mars is not habitable, without only 1/100th of atmosphere only there on Mars. Whereas Venus with the same gravity has 100 times atmosphere, thicker atmosphere than Earth. What is the processes that make it change? Can Earth become anytime like Mars or Venus due to some geological activities? What are the processes that actually make life sustain on Earth and doesn't sustain on planets like this? And these are important questions. Humanity should find answers by sending missions to such places. And there have been many missions in the past, and India also should put our foot forward in finding out, contributing to these domains. And I am very also happy to say that there is a space vision has come out of the success of Chandrayaan-3 that long term we will actually land an Indian on the moon. But this is a very difficult journey. We need to build capacity to send humans to space. We should build space station, and we also got an approval for a Bharati Antariksha station, building a new rocket which is much more heavier capacity launcher. All this happened in the last year time after this Chandrayaan-3 success, and I am really happy that we triggered all these activities in ISRO. The country and many labs and institutions are collaborating and cooperating to build this capacity for us in the long term. So with this, let me conclude and thank each one of you for the patient listening. I believe that some elements of what we wanted to highlight, the innovation elements, the technology elements, what science that has come out of it has been brought out in my presentation, and this all came because that we collaborate globally and work with multi-institutional capacity, including education institutions and research labs and industries in this country. With that, let me thank you. And this picture is so important that this is a picture is one taken by a rover, the lander. Without this picture, you would have asked me a question whether the lander is still landed vertically or not. I think fortunately we got such a nice picture using the rover. There are many more, but then this picture has become a classic picture showcasing the successful landing of Chandrayaan-3 on the moon. Thank you once again.
So thank you. But you will be answering.
If there are any.
I need one of or you can use this. So, Shunat. Yeah. So, hello, Shunat? No, it's not working. So, anyway, now you can hear me. So, the session is open for questions and discussions. Yeah, thank you very much. So, okay,
Am I audible? Yeah. So, sir, I have a very specific question. So, we did a part of the simulation based on the ISRO supplied data, and I'll come straight to the point. This is regarding retargeting on minor hazards at 150 kilometers, 150 meters from the ground. Now, with an active, you see from Chandrayaan-2, Chandrayaan-3, and Chandrayaan-4, you probably we are probably planning for trajectory refinement. Okay, so use the earlier trajectory for the next one and all that. And we now have a DEM probably of the digital elevation map of the landing site. Now, the question is that with an active moon, how do you assume that the boulders will remain in the same place? If there are trimmers there, so can you actually do away with the hazard detection phase where we, go around and go around and take a picture from all sides? And number two question that I have in my mind is that about the gravity of the moon for the lunar pseudolites, the satellites and whatever. So it is not mapped, and therefore the atomic clocks have to be designed. So is ISRO thinking anything about the lunar gravity mapping?
Yeah, it's okay. Yeah. The first thing is, and I fully agree with you, that we should not do so much pre-mapping of the zone in the future missions. We should be able to do this on a dynamic way, looking at the images and take a decision on landing. But then it is good to define the landing sites a priori, because every place is not good for landing because of the density of the boulders distribution, which is very key to make sure that we should identify a safe landing site, but if it doesn't happen, you should be able to make a decision. And I know current algorithms are capable of doing it. The image processing algorithms are very strong enough to detect and then identify landing. This is not going to be a problem in the future. once you understand the nature of the images and the nature of the boulders, I think it should be done. Second, on the topic of gravity, I think all of you know that the gravity of the moon is such a complex one. It is not like Earth. It doesn't have a very uniform distribution. Earth is also not uniform. Earth also has its own harmonics. But gravity distribution on moon is much more complex in nature, and it is much more varied. For example, is for a 100-kilometer orbit itself, the orbital perturbation itself is more than 5 kilometers.
Yeah.
So such a wide geometrical perturbation, capturing it is so crucial if you have to successfully dock in the orbit of moon and land on the moon. But then mapping gravity is complex because we need to take a instrument of that class to sensitivity to that place, because payloads are precious. Possibly when you have a bigger rocket, this can be talked about. In the current capacity, we are not in a position to carry such instruments of precision measurements of gravity. Even on Earth itself, you know, measuring gravity in that accuracy requires ground-based instruments. Space-based instruments are not capable of doing it at this moment to an accuracy that is needed.
Yeah. Okay, sir. Thank you.
I've read in papers that other countries have sent some microbes and some fungi and etc. and to see what happens in space. Do you have any such programs, or have you done anything like that?
You don't have to go to moon for it. You can go to space for it. So what you do is, when you go to International Space Station, we can do such experiments. Possibly, you know, recently Shubhanshu Shukla went to International Space Station as one of Indian astronaut. He carried 5 instruments, and three of them were built in India, primarily biological instruments, which include seeds growing, genetic changes in some radiation, and biological experiments were done. Okay, so this process has just started in India. So recently ISRO had a workshop on biological instrument design and development for future space exploration. So this process just started. There were not many institutions in the country who are microgravity and radiation linked biological changes measurements were not very active, but they have now made a very active. Possibly more useful experiments will come. One of them is related to medicine synthesis, like crystal formation of chemical molecules, which is aided by microgravity. Second is about genetic changes due to radiation, triggering faster genetic change due to radiation in space, and then deriving benefits out of it, especially seeds and food, etc. Third is about biological changes due to microgravity and others. So these areas, research and work is going on. There are a lot of collaboration happening.
No, see, the reason, sorry, I asked this question is, Shukla Singh, I read in the papers, you know, I was thinking that is anything different is expected if it is done on moon?
On moon, I don't think that anything specific is going to happen, because moon is again in space only, and you have a gravity of 1/6 of Earth, so gravity is not going to help us. There is going to be gravity.
Okay.
If you have to derive benefit out of space, you should go to a zero gravity field or a microgravity field, and also we need to have a field where there is a significant amount of radiation. Even if there is a body like moon or Earth is there, it traps radiation.
Okay.
So if you want to really take a benefit, of course atmosphere is not there, but still it has its own disadvantage of. So moon is not going to help you in great way.
Okay. Thank you very much.
Just one more question because he is in a hurry, please.
Hello. This nuclear power devices like nuclear reactors in the known environment of Earth have unfortunately often faced accident and leakage. So in this context, my question is that in the unknown, half-known condition of moon, what precautions are being taken for nuclear power devices? Although, of course, power is less, much less, that I admit.
Now, currently the RTG, radio isotope based thermoelectric generators, are low power devices. They work in terms of isotopes, which radiates and generate thermal output, and using Peltier effects that is actually generating power. And the power is actually very small, like 100 watts and things like that. And there are compact units which are used in long-term space missions like the Voyager, etc. So, but then using nuclear reactors as a nuclear fusion to generate power is not easy. It has been done in the past in terms of rockets. For example, there are rocket cycle, thermodynamic cycle developed with nuclear fusion and using hydrogen as a coolant, and then generate the hydrogen at a high temperature and then expand through nozzle. Engines were built by Russia and America. But later it was discontinued because of the same issue of radiation and pollution of the upper atmosphere. But today, the idea of compact nuclear reactors are being developed because of the high safety along with that, and possibly this will find place in moon soon. This much I can tell you, but further we will discuss later because of shortage of time.
Sir, I have an query. As a sensor biologist, I want to know whether ISRO requires some small point of care sensor system which will be very beneficial in space.
What
and
sensors?
Any type of biological healthcare medtech detection system or any environmental detection system which ISRO till date don't have but you require.
We can discuss. We have a lot of things already there. You may not know that all the sensors in rockets and satellites are actually designed and developed by ISRO in-house,
Okay.
built by industries, including pressure, temperature, vibration, acoustics, accelerometer. Anything you tell, it's actually designed within ISRO. We are not buying it.
Okay.
So we also have technologies for gas detection, elemental detection. All these instruments which I showed, spectrometers, everything are not purchased instruments. They are designed and developed and built inside ISRO.
What about the optimization condition? If it is okay here, it will be okay in space regarding the pH, the temperature?
No, it has to be tested in corresponding environment simulators. There is something called space simulators.
Okay.
We do, even satellites are tested in deep space simulators where we create vacuum, radiation conditions, etc. in large chambers. There are huge chambers which actually simulate space, and we test them.
Do ISRO work in collaboration with other educational institutes? Or
Yes, plenty,
Yeah, yeah.
plenty.
Okay, okay.
There are a lot of work happening. Of course, we can discuss separately.
Okay,
Yes.
okay.
Yeah.
Thank you. So
Congratulations,
we
sir.
have to stop questions, but I'll take liberty. Since I'm on stage, I have one question. Sir, why did so this is my privilege. So because you were in lunar orbit, and we have seen majestic pictures of Artemis, but we don't see any Earthrise pictures from your mission. Why is that? We need a human interference to have the camera for the Earthrise. Because this picture is not real, right?
It's not real.
Yeah, I know. So that's what I was thinking. So why couldn't you put a camera facing the Earth? I mean, it's always nadir, right? Your camera is facing niche. No, I'm not understanding the engineering part at all, but I don't know why that picture doesn't come from our missions, your mission.
I can only suggest you, if you want to see the pictures taken from Chandrayaan-3, you go to, there is a site called ISSDC, Indian Space Science Data Center. If you register as a user, you can get all the pictures, including science data.
Including the Earthrise? No.
Whatever pictures are there, which includes huge amount of data of Chandrayaan-3 imaging Earth, Chandrayaan-3 imaging Moon, landing views, all views, thousands of pictures are there. But unfortunately, like NASA, we are not good at publicity and stories making. So it's more scientific in data. If you are really keen, you can get it. There are hundreds of users across the world who actually uses this data.
Thank you so much.
Thank you.
Thank you. So may I call upon our president? Please wait. May I call upon our president to come up? This time I'll go there and give. He always insists that I also hold. So. You do there. I will hold. No problem. Thank you very much. Thank you very much. Wouldn't you join for lunch? Yeah. So now we'll break for lunch, and then we'll be back in an hour. Okay, whatever the time is, we'll just be back in 1 hour. Okay.
Lunch in 9th floor cafeteria.
9th floor cafeteria. So all of you move to 9th floor. কোথায় গেলেন?